So good morning to all the esteemed participants and our esteemed resource person. So we are going to start session 5, and the topic of this session is tunnel fates, and that will be delivered by Professor Chandan Kumar Sarkar, so from Jadavpur University. So may I take the privilege to introduce Professor Sarkar to our participants. So Professor Chandan Kumar Sarkar is working as a professor in the Department of Electronics and Telecommunication Engineering in Jadavpur University. So he has received DPhil degree from the University of Oxford, UK. He was the postdoctoral research fellow of the Royal Commission for Exhibition of 1851 and a Clarendon Laboratory, University of Oxford from 1983 to 1985. He was a junior fellow with Wolfson College, Oxford. He held the graduate award at Wolfson College. He was a visiting fellow with Linköping University, Sweden, Max Planck Institute at Stuttgart, Germany. He has joined Jadavpur University, Kolkata in 1987 as a reader in the Department of Electronics and Telecommunication Engineering Department. He became a professor and head of the Department of Physics and Dean Faculty of Sciences with Bengal Engineering Science University, Howrah, which is presently Indian Institute of Engineering Science and Technology. And later he joined Jadavpur University again in the Department of Electronics and Telecommunication Engineering as a professor. And since 1999, he has been the professor in the Department of Electronics. So he has published more than 250 research papers in the journals of repute. He has guided more than 250 PhD candidates. He has served as visiting professor in many universities such as Tokyo Institute of Technology in Japan, Hong Kong University, and he is associated with University of La Plata, Argentina, supported by Third World Academy of Sciences. He was an INSA Royal Society visiting scholar at several UK universities. He has served as a chair of IEEE Electron Device Society, Calcutta chapter, the vice chair of IEEE section. He is serving as a distinguished lecturer of the IEEE Electron Device Society and has been invited to several countries. He also served as editor to MOS Devices and Technology section of IEEE section and Electron Devices. He is the vice chair of IEEE Electron Device and Society, SRC Region 10, and chairperson of IEEE Calcutta section. So I welcome Professor Sarkar sir for this session, and may I now request sir to deliver the talk.
Thank you, Manas, for your elaborate introduction. Before I start, I have some words to say. I am really grateful for your invitation to present myself for this FDP. And also, I would like to add your present HOD, if I'm correct, and the Kandarpa Sharma.
Yes, sir.
I have associated myself with this department through his project. So it's really a great pleasure to be here and presenting my talk to the FDP, which you have organized at the Assam University, Gauhati. And it's really pleasure for me to deliver this presentation, which is in this FDP. And I would like to thank all the participants and the organizers for this occasion. So with this, I would like to start my presentation. Let me share my slides.
Yeah, sure, sir. We are really very happy that you have consented to say present here to give the talk.
Okay. Sorry for my throats. Before I start my presentation, I would like to have few words on my presentation, which will probably explain the things which I intended in this presentation. As you already know, the semiconductor is a very important material for people who are involved in electronics, particularly these electronic devices and application. Now, later on, this has taken a very great sort of contribution in the area of very large scale integration. I'm sure many of you all know about it, but I may say a few words before I start. That very large scale integration, the VLSI so called, is a very important field at the moment in semiconductor industry. If I add, recently, as you know, worldwide there is a tendency to uh, have this electric car. An electric car will be operated through the semiconductor chip. And I might tell you that the countries like Korea and Taiwan, they are investing a huge money in this industry of semiconductor to develop the chips, semiconductor chip, which is the key element for the many system which will be required for the electric car. So semiconductor industry is really the future of the, because you already know there is a climate change this conference which is going to be held in UK next week or something like that, and the people are interested to develop the greenhouse free. That means the the uh, the carbon dioxide emission free the car, which is like electric car. It is a big project which is coming big way, and there I find the semiconductor has a very big role to play. So I thought this semiconductor, this industry, we should review it. What is the need and requirement of the semiconductor industry? As you know, very large scale integration is one of the key development in this semiconductor industry. If I go back a little bit behind, as you know, uh, after 1948, when Bardeen and Shockley discovered the transistor, it really changed the face of the all electronics devices and everything. And these transistors are the most key element for development of the semiconductor industry. Now it is going ahead and ahead. Now we have reached to this stage where we don't need any discrete devices. We have a very large number of integrated devices, which we call integrated circuits, and the technology behind is now known as a very large scale integration, and this is the objective of the future of the semiconductor industry. Now, something I want to say before I move, that now this presentation I have prepared just a very preliminary. I won't say I can cover everything, but what it is here, you see that this field effect transistor, which I talked about, the transistor invention in 1948, which was of course bipolar junction transistor, then that was later developed field effect transistor. Field effect transistor has played a very key role in many devices and circuits. And then we went on developing different type of field effect transistors. Now, most common, everybody who are part of the electronics teaching or maybe doing some work in electronics area, the this MOSFET, which is metal oxide semiconductor field effect transistor, which you have read in your undergraduate, and this is the transistor which has become the key element, or rather the foundation of the the very large scale integration devices. Now, this device, which is more in abbreviated, is called MOSFET, metal oxide semiconductor field effect transistor, which is a very important device, particularly for all the integrated circuits, because integrated circuit needs few things which MOSFET can fulfill, which I will show in a later in my slides. Now, what happened that people are always going on development, and the pace of development is going fast and fast. Now, people started with the MOSFET, single MOSFET, then the integrated MOSFET in a circuit. Now, the integrated circuit, which is using very large scale integration, can have 10 billion transistors. Can you imagine the figure? 10 billion transistor. Such a large number of transistors were necessary to develop the big systems for communication or for space technology. So MOSFET played a very important role. And then, everything has its limitation. So MOSFET devices which were used in developing very large scale integration, people found after some time it saturated. There were few things which people or engineers or scientists could not control. These really stop further development. So we human beings are always innovative. So we don't want to stop. If there is some limitation with the MOSFET, people try to develop something which we can get, which can counter the MOSFET, the limitation with some other type of devices. Now, for that, this tunnel field effect transistor, this is also field effect transistor, tunnel field effect transistor. This has been developed to overcome certain difficulties arising out of the MOSFET circuits. So this TFET, tunnel field effect transistor, is really something which has been developed for last maybe 5-10 years. It is to counter the uh, limitation which you find for the MOSFET devices. Now we need to have certain device design and simulation before we can start in making a device. The question is, why do you need a simulation? The thing is that these device fabrications are always very expensive. So we have to sort of simulate the device, rather design the device on paper before we can fabricate, because the fabrication is a very, very expensive. So simulation is very important for all these. Even it was important for MOSFET. People developed all different sorts of MOSFETs or the modification, and the necessary thing was to simulate the device and have the design, because before we fabricate, these design and simulation has to be perfect. Otherwise, because device fabrication and simulations, although it is good for PhD work and research, but when you go to industry, you have to be perfect, because you cannot afford to have a design or simulation which is defective. So there has been a lot of effort, or a lot of analysis have been done for simulation and design, and people have used TFET devices to counter which were the limitation of the MOSFET for future application. Now, in this presentation, we will give you some literature review why TFET would do better than MOSFET. And even if I'm saying TFET is now putting some kind of alternative to the MOSFET, but this still has certain limitation, which whether we can remove it or we can improve it on it. So that is also an issue for researcher, for scientists, for the technology people. What are the things which are needed to counter the MOSFET? Of course, the TFET was developed to counter the MOSFET, but then with the TFET also some limitations were there, and we'll talk about that. And that's why we have a literature review, and we will have a simulation. I already told you, simulation of semiconductor devices is a very essential thing, because before we fabricate, we want to simulate the device. Mean we theoretically fabricate the device in computer, and then we optimize or make it perfect before we take it to the foundry for fabrication. So these are the issues which we will be discussing in the present talk for TFET, how TFET has taken over MOSFET and how it is providing better future over MOSFET. And this is my plan of my talk. Now, this is the quantum computing, as I know the topic. As you know, the nanoscale is a word which is a very catchy word. Now, as I've said, after 1947, when transistor was invented by Gordon Moore in Bell Laboratory, then there were a lot of speculation about these transistors, and actually this invention of transistor has changed the face of the electronics what we have today. that we are having lot of the integration of the transistor. Now it is reaching to more than 10 million in numbers, and this, and also we are having the word which is used as the scaling. We scaling the device. Why we are scaling? Because we want to put these devices in a small chip. The dimension of the chip is not very big, so we have to put lot of these devices and we have to scale them. The term scaling is very often used for the nanoscale electronics, because scaling means you scale the device, rather you control the device dimension so that these devices can be put in a chip without affecting the performance. And then it becomes, uh, because you want to put so many chips. Now question you may be asking, why we are putting so many chips in, so many transistors in a chip? The reason is this: these transistors are necessary for the speed, other functions like amplifications and other things. So these dimensions of these devices can reaches to 100 nanometer. So scaling means that you scale the MOSFETs which are put in for VLSI circuit, their dimensions reduces, and that reduction is a part of the requirement that you have to accommodate so many transistors in a chip. And these transistors are put to increase the memory of the chip, because these days you need a chip for a computer which has a very large memory, and that is it, that you put these chips, the dimensions of the less than maybe 100 nanometer. Now it is, I've talked given you here it 100 nanometer dimension, but now we are reaching technology to 20 nanometers. So you can imagine how fast we are moving in MOSFET, which are being used mainly in the integrated circuit or VLSI circuit. And the thing is that we are going on increasing these chips, so that complexity is going up and up. Complexity is going up and up means complexity is increasing, and this complexity requires so many things. Now complexity, when you put so many chips, so it is a transistor in a earlier slide I've shown is more than 10 million or reaching to billion, and you have to design the, you have to fabricate the device with less than 100 nanometer less. Now it is very easy to say we will fabricate a MOSFET less than 100 nanometer, but question is that is it so easy when it comes to fabrication? That's why I've said in the beginning, we have the possibility of simulation. We can simulate the device, take it to less than 100 nanometer, but fabrication, there are many issues will come. So I have said these fabrication difficulties are very, very major difficulties which arises in the fabrication of very large scale integration. And then question the physical operation. Once you put these devices in a chip, dimension less than 100 nanometer, with this small dimension, there is something which we call quantum mechanical effect. And that is why you have these quantum computation, other things. When you reach to this dimension of 100 nanometer or less than that, then classical physics does not work very well. So you have to have an understanding of quantum mechanics. And further, as you have earlier heard, that this is the FDP on the quantum computation. Quantum mechanics comes in, is, is coming effective in these devices because the dimensions are very small. You may have read in your earlier uh, sort of very earlier part of electronic devices, when you confine the electrons in a very small dimension, the behavior becomes quite different from than a free electron. Why that is? That it is because of the quantum behavior. Now many of you must have heard that if you confine the electron in a box whose dimension is very small, how small? Maybe it is 100 nanometer. So once it is 100 nanometer or less than this behavior of this electron is quite uh, different from a free electron. This idea is a great idea which has been used by the device people, using these new devices which are of the order of 10 100 nanometer or less than. Then you have to have the quantum concept to operate these devices. You must have heard when you confine these electrons in small dimension, then you come out with some new devices which we call quantum well. Quantum well is something when you have two different semiconductor of different band gap and make a interface of this device, and you can confine the electron in a well. And this quantum well, when you confine the electron in the quantum well, the behavior of the electrons in the quantum well will be quite different than the free electron. Free electron means when dimensions may be 1 micrometer or more than that. But the behavior of these electrons, when you confine them in a small dimension device, in a structure which is rather, I would call it rather structure, which is 100 nanometer, and this quantum well behavior is quite different from the bulk material. So if you take a quantum well of gallium arsenide and you take a gallium arsenide material, the behavior of electrons in gallium arsenide, and take the behavior of the same electron when you confine into the quantum well, you will find hell of a lot of difference. The first difference, the energy respect of these electrons which are confined in the, this idea has been utilized by many researcher, and they develop this idea of new devices which are used in MOSFET of these dimensions. And MOSFETs, as I will show you in the next slide, that basically a field effect transistor. And let me show you. This is the structure which I was talking. This has become more popular for VLSI application. This is a field effect transistor. Why it is a field effect transistor? I'm sure you tell your students. It is the, you control the channel. Channel here forms between this this thing between this end and this is, one is called source, another one is called drain. This type of structure is known as MOSFET. MOSFET, why? This is a semiconductor which serves the field effect transistor, and then there is an oxide in between, you can see, that is the insulator. This is like a capacitor structure, and the MOSFET is the key element for many VLSI devices, and these devices are the key element. Now you scale these devices to now 100 nanometer. Once you scale the devices, when they making the device less than 100 nanometer, the behavior of the device becomes quite different from it is a large device, right? When the distance. So here what we want to say about it, that if we have the source drain much close to each other, the behavior of MOSFET will be quite different compared to a MOSFET where source drain, they are quite far. So this idea is used. So one we call a long channel MOSFET, and when they are close to each other, then we call it short channel MOSFET. And this MOSFET is basically the key element in the in developing the all the integrated circuits. So it's, you are putting billions of MOSFETs, which I'm calling a transistor in early my slide, and this is utilized for increasing, making the memory circuit, making the amplifying circuit. So this is the obviously a very important issue for VLSI, using these MOSFETs in an integrated circuit. There you are using very large number of MOSFET. So let me show you how the MOSFET structures. So you apply a gate. So gate is something which controls the channel. Now let me show you these black ones are the channels which is controlled by the gate. So it is very much like a capacitor structure. Now the channel is formed between source and drain, and then you control it with the help of gate. And this is the device which we are using for making many type of circuits, whether it comes to memory circuit or whether it comes to some amplifier. So it is the basic element which is used in VLSI circuits. So this MOSFET has been used very often, or rampant rather I will say, in VLSI circuit. But as I said in the beginning of my talk, my intention is that everything has its limitation. So MOSFET, although it is being used for the fabricating the integrated circuits, VLSI circuit, it has certain limitation. Now for overcoming that limitation, we would like to develop something which can overcome the difficulties which we have faced with the MOSFET. So, so that is the objective of the present talk. So we are here uh, showing you the MOSFET. You know, many of you know how the MOSFET works. There's a gate. You apply a voltage to the gate. Gate will control the channel between source and drain, and you can allow the channel to operate. You may stop the channel to operate. So this is a really a very simple application I'm showing here. But MOSFET, you can make many sort of many circuits, which is the part of the integrated circuit. So this is the basic element MOSFET which I have shown here. Now this has certain difficulties which I will show you, and how these difficulties has been overcome. The device which I am proposing here is the tunnel FET, how it takes uh, how it overcomes the difficulty you face with the MOSFET. Now, MOSFET, which we have used in many integrated circuit, today's VLSI circuit, MOSFETs, as I told you, we are using in the tune of 10 million to 1 billion. So you can imagine such a large number of MOSFET, and that's why you want to accommodate such a large number of MOSFET in a chip. The dimension maybe chip maybe 2 inch or something like that. So you have to scale the devices, meaning you have to put as much as MOSFET in the chip so that it can perform, it can give you many functionalities. Basically, the term which we use here in very large scale integration is the functionality. So you can use many functions out of MOSFET. So you can have this MOSFET because MOSFET offers you packing density and chip functionality. Here, the two terms I'm using, one is called packing density, means you can put more and more MOSFETs to get better and better functions, means more memory, etc. And it can increase the device current and speed. The MOSFETs are used in these VLSI circuits to have a higher speed of operation, and this is very important issue, having a higher speed which you get through the MOSFET and scaling the MOSFET. And then MOSFET is the something which is now this thing I think which is I should give you a very small introduction there. Because of this large scale integration, now it has made the system, or rather chip, very cost effective. Now you get any computer system very low price, low cost, particularly because you can scale the MOSFET, you can put large number of MOSFETs in a chip, and that gives you a lot of functionalities. That's why it is offering you a lower cost. So what I want to say, we can MOSFETs were ruling the uh, VLSI circuits because of certain these three advantages which have been shown here, that you can pack the devices, you can put the very large number of devices in a chip. Here you are talking about a billion or 100 million transistors in a chip, and as you put so many chips, so many transistors, it gives you better functionality, rather better many operations, and it gives you much higher device current, and it is cost effective. The cost effectiveness is a very important. Why I tell you, because this is the reason this cost effectiveness of this integrated circuit has made many devices, many device applications becomes very cheap. Now you can imagine the transistor, the television which were costing maybe 10 years ago, now the same television is costing much less, and you can have many other systems, the cost is going down and down, and this is the very big advantage of MOSFET. So, but as I said in the beginning of my talk, that MOSFET is offering you a lot of advantages, but then one stage comes, there are certain limitations. We'll go into that and how these limitations can be overcome with this new device which I will talk about. Now, MOSFET is, this is just a, I'm showing you how you device scaling. Scaling means how you reduce the dimension of the device, and then you also reduce the dimension of the supply voltage, and your device, the MOSFETs were going below the 100 nanometer, and you have certain technological things which you have to use for going beyond that 100 nanometer regime. Now, power consumption, once you make the device very small, there are two issues for the power consumption. One is called dynamic, when power device is operating, and then that is called static power consumption. So it depends on these two factors, that is C oxide capacity associated with the gate, and then VDD is the supply voltage. These power consumptions is a very important issue when you scale the device. You cannot go on scaling the device without giving, because the power consumption you have to take into account, because power consumption is a very important issue when it comes to making any system. Power consumption you have to control, so you have to control with these parameters like oxide capacitance, which is capacity associated with the gate, and VDD is the supply voltage. So you are interested to have as much as low power here, have to have low VDD, which is supply voltage, and the leak current. Leaking current means you want to make the device smaller and smaller. So what happens is that there is a reduction in the gate oxide. The oxide thickness goes down, and this ultimately uh, provide, generate some leakage current, and that leakage current is not desirable. So this is two issues which come because of the scaling. One is the leakage current, another one is the supply voltage. So we have to consider these two parameters, and you will find that this becomes sometimes a limitation when you go further, making the device smaller and smaller, which will cause uh, to have lower supply voltage and thinner oxide, and that means you have you have a suffering from the leakage current, and this is the ultimately limitation which you'll be facing with the scaling of the MOSFET. But I'm afraid to say that the MOSFET scaling is more required, because our intention, not our intention, the industry's intention, they want these integrated circuit to have as much as functionality possible, and this to have many functionalities you have to have a small devices, mean you have to have scaling of these MOSFETs which you put in a chip. So there is a challenge here you have to face with the MOSFET. Now you can, how you can overcome, we'll see to that in a minute. Now these are the same thing which I've said, that there is some possibility that when you have a gates of the VT variation, means VT is a threshold uh, thing, and we have a term called short channel. Now, as I already told you, you scale the device. If you look at this MOSFET, now let me go back to the MOSFET figure to let you know about that. Now, here scaling, there are two issues here. Now, source and drain, you bring close to each other, right? And you have a gate which is here. Now, when you have a scale source, you squeeze the device like laterally, or you can squeeze the device longitudinally. Now, when you bring the source and drain close to each other, what is the problem? Problem issue here is drain and source, they come close to each other, they start to interact with each other. But that is not you required. Why? Because it's a field effect transistor. What you want the current between source, which is here, which is sending the electrons from source, sending to the gate. The current should be controlled by the gate, because as I know, as you have been told in your undergraduate study, that this is a field effect transistor, current between the two terminals will be controlled by the third terminal. Here is a source drain of the two terminal between which current is flowing. Now that current is controlled by the gate. Now if you squeeze the dimension of the device, between source and drain, what happens is that the source and drain, they start to interact with each other because there is some field arising between them which will interact, and consequent what happens that the gate has no control over the channel, right? This is the very challenging thing about the MOSFET, that when you make the MOSFET dimension smaller or scale the MOSFET, source drain becomes more active. They control the channel current, let the gate remain redundant. So gate has very little effect on the channel. It is the source drain which becomes most effective, and that is not required because you want to use MOSFET as a field effect transistor. You will be requiring gate to control the source and drain. So that is the main objective here. Source and drain should be current should be controlled by the gate. Another thing, when you make the device smaller, that you longitudinally also make the device of, what happens is that this oxide thickness reduces because you are uh, longitudinally reducing. The first, you were reducing laterally, means the source drain was coming close. The second one, when you have a scaling, you are bringing the down the thickness of the oxide, which is also not desirable because that will make the many electrons from the gate to leak through this oxide, and that will give rise to leakage current. This is the another uh, obstacle which you really come across for you scale the device. So scaling may first of all make the source drain redundant, and they have oxide thickness reduced, means it can really cause a what you call leakage through the oxide, because that is when thickness of the oxide reduces, there will be tunneling of the electrons through the gate oxide going into the channel. So these are the very two issues which are affecting the MOSFET operation. One is the tunneling effect, another one is the short channel effect, which is making the green gate and the drain closer to each other. Let me go back to the same where I was. Now here in these devices MOSFET, what you have a very famous term which is called subthreshold swing. It tells you how much faster you can switch the device on and off. So this is the subthreshold swing, which is very important parameter. How with the gate you can change the threshold voltage, and this is the called very important parameter, subthreshold swing, and this determines very important aspect of the MOSFET, because this tells you how much leakage will be possible through the gate oxide. So subthreshold swing, which is basically tells you the leakage, which just now I told you, the gate thickness reduces, then there will be actually tunneling current through the gate oxide. And there are other effects like velocity saturation, because there will be increase. There is a two field, one field from gate to channel, and there is another field which is between gate to source, which is called lateral field. This will try to control the mobility, and then there is the effect of charge sharing between drain. This is called short channel, and there is the other effect, hot carry. So these are effects which are arising in a MOSFET because of the scaling, meaning bringing the source drain close to each other and bringing the gate oxide down, and thickness of the oxide less and less. So what I want to say here, so MOSFET, although it is offering very great uh, help in developing new system, but it has certain disadvantage like subthreshold swing, another thing which I will explain it to you further in much more detail. And short channel effects is term very often used, which I explained you, that when you scale the device, you bring source and drain close to each other, and then the gate loses the control of the channel. That this thing is called short channel effect. And this is the thing which is very challenging for the MOSFET to be used for future very large scale integration. Now, as I said that what is the alternate solution to CMOS scaling problem? Scaling, which I explained you, make the dimension smaller. Why? Because CMOS dimension, if you don't make it smaller, you cannot accommodate many transistors in a chip, and these number of transistors you required for complicated circuit requirement, whether it is a memory, whether it is a sort of this thing, memory effect and other amplifying effects. So these are required. The scaling, ultimately you have a limitation. You cannot go on increasing the, or rather decreasing the size of CMOS, because it causes some problem. So what is the alternate solution of CMOS scaling? Because CMOS scaling is essential, because you require CMOS, because as per requirement of the industry, because you want more memory, you want more speed. So these are something which you cannot avoid, and that is the technology. So how to overcome this CMOS scaling problem with the existing technology as we know? So we will talk about that in a minute, how much you can overcome the CMOS scaling in your thing, which you overcome as much requirement of the industry. So CMOS scaling, which I explained you, it is means that you make the dimension CMOS smaller and smaller, so that you can accommodate more and more these CMOS transistors in a chip, which will provide you more memory, more speed, etc. That is the requirement of the industry. But when you put these devices, you reach to a limit. And what you do when you reach to the limit, how do you overcome this? And that is the what we are going to show you here. What is the alternative solution to this? Now we divide, rather we will propose tunnel device. I'm sure what is a tunnel device, you know a little bit. You have heard tunnel diode in your undergraduate electronic devices circuit. So it is based on tunneling. Tunnel is something conceptual. It is not observable classically. So we call it a tunnel device. And you remember your tunnel diode, which is a heavily doped PN junction. There is a tunneling between from the P to N. There is a tunneling. Always there is a heavily doped junction. There is a tunneling, which is something which I will explain in a minute. Uh, this arises in this type of band structure. As you see, this is a conduction band. This is a valence band. This is here. When there is overlapping between these two, and there is a flow of electrons from the here to this thing. So what happens in the tunneling? Let me explain you. Now, as you see, that there is a barrier, and this is what you call it quantum mechanical phenomena, that you do not have any, you cannot give you an example of classical physics where tunneling taking place. Tunneling means this electron here, as you can see, can tunnel through this barrier, which is looking the green one. But when the barrier is wider, it cannot go. You require an optimum width of the barrier, so that electron can pass from others, one side to other side. This concept of tunneling is called quantum mechanical phenomena, which doesn't have a classical analog. And using this idea of tunnel FET, people have developed some new devices which you call tunnel FET, and this tunneling is the alternative to the MOSFET. I will come in a minute how it becomes alternative. Why tunnel FET? Conventional MOS devices have a problem of that minimum subthreshold swing is, as I said, that is 60 millivolt per is required for subthreshold swing. What is a subthreshold swing? It is how fast voltage will change compared when you change the gate. The device, drain current will change, changing the gate voltages. So TFT has advantage, that a tunnel FET has advantage, that is not limitation of 60 millivolt, and you can have lower subthreshold swing. In the case of MOSFET, this subthreshold swing cannot be reduced below the 60 millivolt. Here it is much lower than that, and that means, as I told earlier, the subthreshold swing gives you a measure of the leakage current, and we can have lower leakage current with the this thing, and then you can have a lower operating voltage for the tunnel FET compared to MOSFET. MOSFET, you cannot go because of this limitation of subthreshold swing 60 millivolt. That is the minimum subthreshold swing you require at room temperature to obtain improved performance voltage. One need to design device with more reduced subthreshold. So you require a reduced subthreshold swing, which is not possible in the MOS, but TFET, the tunnel FET is more appropriate for this, and the leakage power is much more less here compared to the MOSFET. So that makes the TFET. So if I make it more clear, the MOSFET has some limitation because of the subthreshold swing. There will be some appreciable leakage current. Why it is not the case in the TFET, tunnel field effect transistor? So it can overcome MOSFET when you are going for a low voltage application. That is something very important. Sometimes you have to develop some circuits with a low volt application. Then tunnel FET will be much better because of the lower subthreshold swing, which is much less than 60 millivolt per decade. So this device, which will be made with the TFET, in comparison with the MOSFET, it consumes a low power because of, as I told you, that 60 millivolt, the minimum voltage needed here in the case of MOSFET is a 60 millivolt per decade to change the threshold swing, but TFET, it is not the need, and you have TFET due to presence of large potential barrier in off state. So because subthreshold leakage is less, there is a large potential barrier, which I will show you in a minute, that this device is much more suitable. So if I read it, tunnel feed effect transistor is a type of device which main principal operation based on principle of band to band. I've shown you there was a tunneling going from valence band to conduction band or conduction band to valence band, and this is the switching between on state off state for low gate voltages. That is a big advantage, which was not possible conventional MOSFET. It was not possible to switch in the case of MOSFET with a low voltage. Therefore it is expected that device can operate low power. So if I make a summary, that MOSFET, because of the subthreshold swing, which is the need of the device, you cannot make it switch at very low voltage, means it cannot be operated. MOSFET cannot be operated. Conventional MOSFET will not be operating at very low voltage, while it is possible in the case of TFET, much less power. That makes it more, because many of the devices, many of the circuits, you require very low voltage for switching purpose. So that requirement is satisfied with the help of TFET compared to MOSFET. So MOSFET, although it's a very versatile, it has been used many applications because of its operation requirement. It cannot go to very small voltages compared to TFET, tunnel FET. Tunnel FET, because it offers a very different principle. I will show you there are two basic mechanism for these two devices. One is tunnel FET, another MOSFET. So because of MOSFET operation principle and TFET operational principle is different, I'll show you in a minute. That makes the tunnel FET, it can be operated, it can be used for very low voltages, and it consumes very less power compared to MOSFET. It makes very attractive for many applications. When it comes to applications, tunnel FET will be more preferred over the MOSFET. So if I, in one statement, the MOSFET, although it's very versatile, it cannot be used for very low voltage switching or low voltage application, while TFET is more convenient to use it because the mechanism of operation for the two cases are quite different. So it is basically operating on the tunneling. Tunneling is what means that electron can move from once without crossing the barrier. Just let me show you once again the same curve. Let me show you this thing, which again to now the electron here cannot go this electron cannot come to this side. It is the tunneling phenomena which allows this electron to travel from this side to this side. So why it is coming? So it is coming that you are using here quantum mechanical concept, which I told you that you are actually looking at the wave picture of the particle. You are not looking the particle picture. So electron wave picture wise, it has a certain probability to reach this end. That is called tunneling phenomena. While classically this electron cannot jump this barrier, come to this end. I hope you understand. One process is the classical process where electron can reach the other side by jumping the barrier. Now here electron will reach the other side by wave mechanical picture. It is the electron wave which can penetrate the barrier, can reach here, and that is the issue here, which are used to apply here. Now this is the will give you the what I have been telling you, how these tunnel FET structure different MOSFET. In my beginning of my presentation, I think I have explained you MOSFET structure. There you have a source drain. Here you also store source drain, and there is a impurity doped structure. This is better short channel effect. I explained you the short channel effect, that you bring the source drain close to each other, so that becomes very effective in the MOSFET. Tunnel effect has a weaker dependence on tunneling, dependence on temperature, because tunneling is something, the quantum mechanical concept. Quantum mechanical means you consider, many of you may be not knowing what is a quantum mechanical concept. There are two issues, two concept, is a particle concept and the wave concept. You consider in tunneling, electron is wave, not particle. So tunneling mechanism is the wave mechanical picture of the system that you consider. That is why electron can cross the barrier, because the wave, possibly wave function of the electrons can have a finite probability one side of the barrier to other side, as I just now shown you. So it is a quantum mechanical concept which is called tunneling. So that quantum mechanical concept is quite different from the classical. So you consider in quantum mechanical concept, this particle is, electron is not only particle, it is also a wave. So you consider electron is a wave, also you also consider as a particle. So tunnel FET uses this tunneling concept. Tunneling means you consider the electron as a wave, and because here you consider tunneling, the leakage is a very low voltage phenomena. You will have, sorry, the because you use it for a low voltage, static power consumption is really very low. So you see the advantages here. In tunnel FET, you are using the wave mechanical picture, so it allows electron to travel across the barrier, which is not possible in the case of MOSFET. And it is a low voltage, so noise will be much less in these devices, and power consumption, that is very important, because many of you electronics students, you know the power issue is a very important issue when it comes to device. Now tunnel FET, when it comes to comparison to MOSFET, it is operating at very low voltages, so power consumption will be much less. So that is the very big advantage over the MOSFET. But there are certain, you cannot get all the advantages, then we will not have any other job to do, because we have a challenge to improve the TFET over MOSFET. What are the shortcomings which we see in the TFET, which can be overcome? So this is, I just wanted to tell you, this is the sketch of the cross-sectional view of the single gate TFET structure. Now I hope you understand the MOSFET. In MOSFET, you have the different analogy. There electrons are working as a band-to-band tunneling. Here electrons are in MOSFET, they are jumping the barriers. Now you can see the physical of, now you can see this is the conduction band, this is the valence band. Now there's a, once you bring it down with the voltage, there is a flow of electron from this side to this side, and that is the known as the tunneling effect, as you see in the so this is the physical operation. Now you can see this thing, there is no flow. So this is the off state, this is the on state. Off state, there is no flow. So on state, off state, you can bring it by applying a voltage to the source and drain. And that has been shown here in the characteristics. So operation of TFET, this is typically PIN. You have a P, there's the impurities, and N tunnel fed. Structure shown N-type device is a P. Now this, you have seen the device which is an N-type structure. Now N P plus source and N plus source, which we have seen. And basically, for your understanding, I may say this is the, if you remember the Zener diode, working principle of tunnel is depends on the gate bias control of band to band. So it is a gate bias which controls the band to band tunneling. In order to generate tunneling across the PIN structure, positive voltage is applied to gate. So you apply here drain and gate positive. So it is a basically Zener diode case. Operation of TFET depends on applied gate bias voltage and drain bias voltage. So these are very important issue. Here you apply gate and source positive voltage, then only you find the flow of the electrons going on. So this is the, so this was a TFET will depend on the gate bias voltage, which I have shown you. It will depend on what gate bias you apply, and drain bias that pulls the electron from source side. So TFET operation depends on applied gate bias voltage and the drain bias voltage. Leakage current flows between source and drain. I think you already, I explained to you. And on state, you are generate with a positive gate voltage to, as I've shown you, positive gate voltage narrowing. There is a narrowing near the source body junction, and there is a tunneling taking place in it. So basically, on state, when positive gate voltage to be applied, and this narrows the junction near the source body junction, source to main body narrowing, there is a tunneling, there's the barrier becomes very thin, so there is a flow of electrons which is going from source to the drain side, and this band to through the band to band tunneling through the drain side. This is the operation. Now this shows this thing, as you can see, there is no overlapping here, there is overlapping, little bit overlapping, much overlapping by the, so this is the tunnel FET characteristics. It gives you much more larger current and this thing. And now again, I want to repeat what I've said. Tunnel FET is a low voltage device which has advantage over the MOSFET, and here it depends on the band-to-band tunneling, so there is not much effect of the what I want to say, this band-to-band tunneling will not affect the operated at low voltages, so that is the main advantage. Now this is something which I thought write down. There is an interband tunneling, drain current flows across the highly doped. So this is just an operational principle which I've explained, and this is the expression GVB, which is the theoretical model for the tunnel FET. If you use it for applied as a function of energy gap, this you can see that will give you the if you integrate, it will give you the tunneling, as it is gives you the drain current if you integrate it over this thing. And this is the important parameter, which is subthreshold swing, and subthreshold swing is the most important parameter. As you can see, it does not depend on KT by Q or KT by E. That makes it possible. It does not depend on KT by Q, not limited to 6. So you can make it less than 60 millivolt per day. That is the not thermal limitation. The limitation In the case of the MOSFET, this depends on KT by Q structure, which limits the operation of MOSFET. This is not the case of the tunnel FET. So sub-threshold swing is much less than 60 milliwatt. What does it mean? It means that you can have much more lower leakage current so that you can operate at very low voltages. This is the sub-threshold swing. That is, you can see the conventional MOSFETs, the gate volt, even at the zero gate voltage, does not go to zero. While in the this thing, tunnel FET, you can. This is the major difference.
Sir, sorry to interrupt.
Sorry, say
Uh,
please.
yes, sir. Sir, probably your presentation mode gets off, sir.
What time I
Right.
have to finish?
No, no, sir. The presentation mode means slides are not visible
Oh,
now, sir.
I think it's switched to. Okay, let me see it again. Just a
Yes,
minute.
yes, sir. Yeah, yes.
I will. Sorry for the interruption, ma'am. Let me see.
No issue, sir.
It has come.
Yes, sir. Yes.
Okay.
Yes, comes.
I think I by mistake I have is this stop sharing or something.
Maybe, sir. Yeah. No issue, sir.
Now I was here. You can see that in the case of here, average the threshold swing is here. It is going here in the blue one and is not going to zero here. Threshold voltage is usually defined as a constant current. So this is the one can one can make it a sub-threshold swing here, expressed as mathematically threshold VTH minus V off. Now, this slide I am going to show you. Now, this is it explains all the what I have said. These are the two structures. One is the basically you can see is the MOS structure. This is the TFET structure. As you can see, this is source, this is drain, this is channel, and now this is the band diagram. Again, this is the TFET structure, which is having channel as a I structure. Okay, it is visible to everyone. Hello, it is visible to everyone. Hello,
Mm, sir, I think it is visible.
it is visible. Hello.
Yes, sir.
Yes,
It
sir,
is
it is
visible.
visible.
Okay. So the main thing was the main topic of the our presentation was to compare MOSFET with the TFET because MOSFET has ruled all the technology so far in the semiconductor industry. Now there's another new device which is basically quantum mechanical device which is called tunnel field effect transistor. Because of the it is based on tunneling, it has certain advantage of being operated at very low voltage compared to MOSFET. And also the TFET has become more attractive because it can operate at very low voltage, because low voltage operation is also very important for many systems. So now you can see this is a TFET structure and this is the MOSFET structure. Now this you can see there is a flow of electron through the jumping the barrier over the barrier. That is the most important thing. And here you can see this is a field state here, and now reaching here the state the electron is tunneling from this barrier which is here through this. So these are two important distinction between the MOSFET and TFET. So MOSFET, electrons are moving more as a more jumping the in the MOSFET. It is now moving like this. Now it is tunneling through the barrier. So that is the main message I want to give. If you want to understand, the MOSFET is the device where it needs a jumping. Here it is a totally quantum mechanical. So temperature dependence will be much less about the functions of the device when it comes to TFET compared to MOSFET. These are two basic difference between typical operation of MOSFET and TFET. As you can see, this is the situation. Now this is the just how the drain current varies between these different drain to source voltages that they are shown here. Now we have something called double gate device. Now conventional MOS, which I have shown you earlier, it has one gate. Now I'm showing you the same device with the two gates. Now why we are having why it is attractive to have a two gates? That's my first question. Now with a single gate, this is a conventional MOSFET. You have a gate, you have a source, drain. Now here you see the two gates, as you can see here, right? So with this, biggest advantage is what is the role of gate? Gate controls the flow of electrons from source to drain, right? It controls the channel current. So conventionally we have one gate. So with one gate we cannot control the electron channel so tightly or rather so effectively because it's one gate. Now if you use the two gate, one on top and one on the bottom, what is happening? It's a logical. If one man fights, it will fight less. If two men fights, it will fight more strongly. This is again the same situation. You have two gates, meaning the channel of the is better controlled by the two gates compared to the single gate. So here also in the we have two gates for the better control that has been shown here. This idea was very often used for the MOSFET. This is used for this TFET. What are the advantage? Short channels. I have already told you what is the short channel effect, that we want to remove the interaction of the source and drain minimum to possible, and that if you can control, that is a controlling the short channel. But short channel effect will come because we want to make the device smaller as per need or as per request of the industry. So better scalability means you want to have better short scalability when you can reduce the dimension much better. Scalability means you can scale the device and lower sub-threshold current. Because of the two gates, the switching of the device, what is you call threshold? The device you want to switch higher on current because it will have a more on current near ideal sub-threshold conditions also, and most of important is the lower gate leakage current. So these are some of the advantages which you are achieve with the help of double gate. So double gate allows you to control the channel better, and once you control the channel, you control the short channel effect, and which is very undesirable. So with the double gate you have advantage. Now this is the conventional double gate structure in MOS, and it has been done in the case of the TFET. You can see I channel, there is source, drain, and gates are here. So this is the basically a conventional TFET structure comparing with the conventional MOSFET. So double gate structure provides you better short channel effect, and that is the objective than compared to the other single gate MOSFETs or single gate TFET structure. There is another type of device which is very often used. This is the called surround gate. If you can imagine that you had the source drain, and then there is in between source drain you have a gate. Now what you want, the gate should control more better way than one strip, which will do in the case of a MOSFET. Here what you have done, surround gate. You have surrounded the gate. This is a source drain in a cylindrical form, and that you allow. So channel will be surrounded all the way round with the gate, and that makes, and this here you can see this oxide which is coming between gate and this cylindrical thing where source drain. So this surround gate structure has another advantage, that it is surrounding the source drain all around, and it gives you much better control of the channel, and that's why we call it is even better than double gate structure. So if you compare the double gate structure with the surround gate structure, it is trying to cover the gate all around, but a double gate structure on the top and gate. So you can visualize there are two situations. One is the top gate, another one is the basically this surrounding it, means surrounding this structure, this cylindrical structure which I am showing through the cursor. Now it is surrounding with the help all gate around, and this is basically advantages compared to double gate structure, and one can also develop the TFET with the help of this new structure. This has structure utilizes a thin body to eliminate the sub-leakage path between source and drain. Very thin gate structure. Thin silicon body leads to tight coupling of the gate potential with the channel potential. So these are advantages which I have just spoken. By surrounding the gate, the channel, the gate has much better control, and it will be having better control of the gate, the channel current, that is most important for the device. So this is done by this all around, means that is which is shown here, that source and drain is surrounded by the gate. This is surround gate structure. Now one effect which is coming in the tunnel FET. Now difficulty with the tunnel FET is this. Has anyone realized what is the difficulty with the tunnel FET? Where actually it is being beaten by the MOSFET. MOSFET has many advantages, but tunnel FET has shown some of the advantages I have already explained to you. But one advantage, still tunnel FET is struggling compared to MOSFET. Can anyone tell? I'm not sure. But the most disadvantage of the tunnel FET is that tunnel FET cannot give you much more on current. The current which is required between source and drain, we call on state current, which is much less in the case of TFET. And this becomes big advantage of the MOSFET in the current rating. The MOSFET has so far ruled over the TFET. TFET given you that it is operated at very low voltages compared to MOSFET. The temperature dependency less because it works with the tunneling. Tunneling is really something which does not. In the case of MOSFET, it is the barrier crossing. It depends somewhat in temperature. Sub-threshold swing, which is another thing which is also not very desirable in the case of MOSFET. But here, on-state current, the current which is flowing when the device is on, in the MOSFET, it is much higher compared to TFET. This is the advantage of the MOSFET over TFET. And now I will show you certain slides, because research is always innovation. You want to improve it. So people have taken job how to improve the TFET in terms of this on current rating. There is some effect which is called ambipolar conduction. What happens is there is sometime power supply exceeds the voltage Eg by E. There is a reverse. What is reverse? The tunneling should be from this side to this side, from the valence band to conduction, but there may be some tunneling coming from this side to this. This is called ambipolar conduction and reverse tunneling, and this is not very much desirable, but it does happen in the TFET. This is something called ambipolar tunneling, which is called reverse tunneling. But we have to see how to, so it is the drain which is injecting the carriers into channel, which is defined as ambipolar. So it is reverse direction flow of the electron. So this ambipolar potential is something which is, it happens in TFET, it is not a big issue. But most big issue which is with the TFET, I have already told TFET very much useful in fabrication because it is used for low voltage and other things. And then the on current in this device is much less compared to MOSFET. What is the remedy? I will show you in a minute. Now question, it is the researcher's job how to optimize the field effect transistor, a tunnel field effect transistor. Now, in the MOSFET, as I told you, because of dependence on the subthreshold swing, AT by Q, you cannot reduce is less than 60 millivolt per decay. Here, you can reduce it. That is the target. By this reduction, what you can do, you can make the leakage current much less. Now, problem in the MOSFET, the on current is much less, and off current is also very low, but also you want to reduce much less low current, but on current you have to make it high, because on current, having higher on current is the ultimately suitability of the particular device for the application. And there are certain optimization technique which you use. We have to have these adapt doping profile, optimize source doping, and small band gap source channel tunneling point. So there are certain optimization requirement we do, but most important thing is to, as I in my talk I have mentioned many times, that TFET has many advantages over MOSFET, but it is beaten by the MOSFET on the on current. As I told you, the VLSI, basically people are using MOSFET because of this high on current. It has not been possible to use TFET to that big way that it has been done in the case of MOSFET, because you cannot increase ion. But there are ways, there are innovation, there are new ideas you can introduce in TFET, and that is what I think is very important, that you look at this thing very carefully, how you can improve the TFET. Obviously, something you can do in case of TFET to increase the on current, which is most important requirement for this. Now, optimization of tunnel field effect transistor, tunneling barrier width, so that barrier width which is between P and the channel, gate and channel, should you want to reduce it and increase the this parameter which I have shown you, and various structural modification can be done so that the tunneling barrier becomes less and less thick. And now most important thing is that you want to use these material instead of silicon. As you already know, silicon is a very versatile material. People have started preparing silicon TFET because silicon is abundant. Now there are materials which will give you higher mobility, and that is ultimately responsible for giving higher modulating current, higher on current. And these materials are basically silicon, germanium, indium arsenide, and 3,5 materials. So these are method which we can use these materials for TFET applications to increase the ion so that it can compete with the MOSFET. Now people have come out with the various modification. One is called pocket doping, something I want to explain, that instead of having a source drain isolated, one can have some additional doping at the source and drain. That is known as pocket doping, or other, which is you call halo doping, and that reduces the short channel effect. Short channel effect means it really cuts the electric field between source and drain so that less interaction happens. Now surround gate structure, which I've already spoken there, by the surround gate you ultimately you have increased the effect of gate on the channel current. High K dielectric means it reduces the leakage current. That is a very common method of using these MOSFET, which is scaled down to very small dimension, because once you scale down to very small dimension, thin gate oxide leads to much leakage. Modification spacer, one can use a higher spacer. I will explain it in a minute. High mobility material, which I just shown you, high mobility material is indium arsenide or the silicon, germanium, or gallium arsenide, these materials will give you higher mobility, and consequently that ion will increase. So obtain high on current, comparable to MOSFET, you have to have material with a low band gap, higher carrier mobility, and the materials which will be important like indium gallium arsenide and 3,5 materials. 3,5 material TFT has been very attractive. People are working. That is a research topic. If any one of you are interested, can go and look at the literature, how people are working with the 3,5 material. Here I am specifically calling out indium arsenide or gallium arsenide materials or gallium indium arsenide material, and for higher mobility. That is the one of the requirement for the TFET. Now there is the another thing is to how to reduce the I of current. This is the structure you use, that is called underlap. So you have a region which is drain and source between drain. So this is the underlap region we call, and lower dropping, and this can reduce the I of, which is not desirable. So this is the structure which you can use for this device. Now, high on current TFT depends highly on the doping material, which I have already explained. Effective band gap of the source body junction, that is at the source, what type of material use. The effective band gap reduces, tunneling barrier becomes thinner and thinner. Now, if you have a large band gap, then tunneling barrier will reduce, and also reduce the ameliorate on current. Rather, tunneling barrier will increase, that it will allow more and more tunneling. Thin tunneling barrier will be formed at the source body junction. That is the objective, and you want to use these material for higher current on current, as I have already explained to you. Now I've used some additional these decided the PPT I've given to Professor Sharma was I added these two. I thought that these are some of the research areas. Maybe you are interested. Uh, this may be useful for people who are really want to move into research area of a tunneling junction. So this is the, you can see that this is the 3,5 material, which is indium gallium arsenide used, and it can increase the drain current, as has been, you can see in this material. So these are some of the listed material which can increase the drain current. Hole density means it can increase the drain. Band gap narrowing produces more band to band generation holes shown in the figure. So this is some research area which you can be, if you like, you can use it. Now I've already, this is the another thing, you want to use it for high frequency application. High frequency performance of MOS transistor, you can use the two frequencies. One is called cutoff frequency, another called maximum frequency of oscillation. Here we have also studied these two. FT is a unity current gain frequency. These are for AC field, and these are some research topic which maybe you are interested, which have cutoff frequency. This is the frequency, the highest frequency device can be used for amplification. This is the maximum frequency for amplification or something like that. So this is just a graph which shows the cutoff frequency in some materials. And you can see again the 3,5 material in indium gallium arsenide is useful. And this is the FT frequency, which is called unit current gain frequency. Now, if it can be used for some high frequency devices for non-linear applications, so these are I have used for two materials, and harmonic distortion. These are some of the analysis have been done for second harmonic analysis, and the third harmonic analysis. You can see these parameter. These are called basically reliability parameter. Harmonic distortion is something which is ultimately responsible for producing noise in the high frequency application. So this is our observation. These heterostructure PFET device with the different source materials are found to provide outstanding RF performance compared to all GTFET. Here I am summarizing what I've just said in previous slide, that PFET, PTFET devices with the different source materials will be very useful. Mild degradation of intrinsic capacitance resistance, transfer delay may occur. Germanium TFT with 3.5 source material is better alternative to RF application. And this work presents a comparative study of NQS. NQS effect, I think I'm not going to much more details, but anyway, this is effect which one can study. This again coming as a more like a advanced topic. So this is something most important one which I want to say, that PTFET devices, which if you work with the different source material, can give you much better outstanding RF performance. Now, many of you are interested how these devices are fabricated. I'm sure if you are already know about it, and already you know the TFET is a tunnel device, and tunnel devices, from your understanding of the this the tunnel diode. This is a heavily doped PN junction diode. Here also you have to use very highly doped devices. It is a heavily doped junctions will be used, and these are some of the uh, techniques which are used for fabricating this device. Ion implantation, rapid thermal diffusion, molecular beam. These are basically some growth technology which can be used for the fabrication technique for the TFET, because you must know how this fabrication is used. Techniques are used to fabricate the tunnel field effect transistor. Now, this is something again very much theoretical research area. Variability means there are certain parameters, something called random parameter and something called systematic parameter. So these parameters can affect the performance of the device. Here, there we are talking about two random parameter. One is extrinsic, another one is intrinsic. I have shown extrinsic parameter as the ion implantation dose, energy, oxidation temperature, and this is the intrinsic is channel doping. So these are some parameters ultimately responsible for the variability of many properties of the device. And there are some systematic variation of the devices are basically wafer. If you choose the wafer, this will give you systematic variation. So this is variability is some research area on this TFT, because these parameters can be varied and ultimately can be studied, the influence of the variation of these parameters. So there are two parameters. One is the random, one is the system random. You can have extrinsic, which is outside device implant dose, etc., and another intrinsic, which is inside the device, like oxide thickness and body thickness, etc. Now, these are again the same thing, which this is called process variability. So, how you use this affect the impact parameters, how this silicon thickness, oxide thickness will ultimately affect the performance of the device. Now, process variability includes the macroscope. These are some of the research topic fabrication which are used: oxide thickness, device body thickness, which will be used for fabrication of the device. This is just some percentage of variation of various devices. This is silicon thickness, this is oxide thickness, how the drain current varies in these devices are shown here. Now, this is called straggle. Straggle is something which is required for ion implantation. You send the ion beam to the device from the source, and what happens? The ion beam spreads out. It doesn't stay at the source. When you want to do it for halo doping, rather doping the source side, So what you can see that here there is a straggle. Straggle means there is a spread of this implantation, and this is called lateral straggle. So ultimately the channel width will be affected through this straggle, and that straggle is arising how because of the ion implantation. So ion implantation techniques are used for making some kind of halo in the devices. So this is ion implantation which you have shown, which we have shown here. As you can see, the different doses which are given here for different tilt angle will be used for ion implantation. This is again the equation which are used for ion source to drain doping, etc. Now, in conclusion, I have following things to say. Tunnel diodes expect to add new another node, means it gives you new avenues over the MOSFET because people are used to MOSFET for a long time. Now, few things which with the MOSFET we cannot achieve. Now, want to see with the tunnel diode we can do that. Now, terminal tunnel devices could be saddled nodes for end of Cmos scaling. So one can have a three terminal tunnel devices, how it can compete with the Cmos devices. That's a very important thing to be seen. Challenging TFETs more practical than following. So the challenging phases of TFETs more practical than theoretical. Here we want to say that you get some challenging facing from TFET over MOSFET is a very important area of research, and rather than it's also offer you theoretical as well as a practical motivation. And the fabrication process also you have to study for fabricating the TFT, lithography, process optimization, ion implantation. In comparison to MOSFET, the ion by off ratio steep S's over several decade indicate. So I've already explained you the ratio ion by I off ratio is the very high ratio, and steep faster changing subthreshold swing. These are two important issues with the TFET. Makes it superior compared to MOSFET only, and allows you to, because of the steep subthreshold swing, allows you to operate at low voltage. Because of the why it is because the low leakage current you can have with the help of this, and it gives you ultra low voltage application. It gives you superiority over the MOSFET. So in sum, if I sum, the MOSFET of course has ruled the VLSI regime applications, but now people are coming and trying to realize there are some issues where MOSFET cannot be used. One should use some new devices. The TFET comes into that, but of course TFET, there are many issues which is not bad because issues are always encouraging. I must tell the people who are attending this the FDP that issues are very good because you have possibility to work in this area. These issues gives you some research problem. This research problem which you get with the TFT fabrication, not only theoretical as well as practical over MOS, because MOSFET has been extensively studied in the VLSI area. So there you can use the TFET and look at the TFET in new prospects of the MOSFET and develop some new ideas using some new structure, new fabrication things. And that is what I want to my message is that. So my message in this present talk is that MOSFET you know have known it for long time. People are working in this era of integrated circuit for long time. So MOSFET has played a very important role. It has given us lot of advantages, lot of facilities, etc. But there are some issues with the MOSFET which you cannot overcome. And then there is a new structure TFET which you can use it comparison with the and compare its performance with the help of compare it its performance with the MOSFET and see how it can be improved, can be can be used comparable in performance with the MOSFET. So with this word, I want to finish my presentation. Thank you for your patience. These are some references. Maybe some questions you want to ask.
So I
Hello.
now request the participants to raise some queries, and if there is some say problem in the audio system, uh, it can be typed in the chat box also. Then I'll read that out.
I just want to say one thing, that the purpose of the presentation is that MOSFETs have been very popular for all the very large scale integration. Now you have the nanotechnology where MOS are ruling. Now people are trying to bring the TFET because of certain disadvantages of the MOSFET. One of the disadvantages, the current is very low in the case of TFET because its mechanism is quite different from MOSFET. I've already explained. It is the barrier jumping. In the case of the TFET, it is the tunneling. In tunneling, the amount current is much less compared to the barrier jumping.
Yeah. Sir, one question from my side. So is there any mechanism to improve the on-state current in the TFETs?
As I said, that is the most challenging one. Is the people who are using the material with a high mobility material like indium gallium arsenide or silicon germanium. If you can increase the mobility, then that will probably one of the way you can. There are other, of course, method where you can have new structures, but ion can be basically improved with the help of the new materials, which can be used for tunnel fed structure.
Okay, sir.
You require a high mobility material.
Okay, sir. Okay. And sir, what is your take on graphene, sir, as a material?
Graphene for what? Making the TFET.
Yes, sir.
I don't know about this development in this area.
Okay.
Graphene has some other, because we have graphene, they have made field effect transistors. They've
Yes, sir.
used it for various circuits and application. It's slightly different from that also.
Okay, okay, sir.
TFET is basically a alternative to the MOSFET, which has been ruling the VLSI era for such a long time. There are some problems that are arising out of the MOSFET. They want to be solved because now there are problems with the TFET also, the current problem which they want to use it. Fabrication side, it is not so difficult because uh, people are using same technology as it is for the MOSFETs also.
Mm. So any questions from the participant side? Okay, so if there is no further query, then we are going to say end this session. So we thank Professor C.K. Sarkar sir for giving us time out of his busy schedule and giving such a nice presentation. So thank you so much, sir.
I hope that this presentation I have added 2 or 3 more some research slides. The one I've sent you earlier, you can keep that one also, or you can copy this one also.
Okay, sir. Okay.
This one has few advanced research slide which I've included, but the one which is not so much different, only 4 or 5 slides are additional in this one. The one I have sent you in mail, you can take that also.
Sure, sir. Sure.
Okay, then thank you very much for your invitation. I'm quite grateful. Thank you.
Thank you, sir. Thank you.